Modern web applications must process thousands of simultaneous network requests, user inputs, and database queries without dropping a single packet of data. To manage this load, it would be logical to deploy multiple processing threads. But JavaScript operates under a strict design limitation. It is a single-threaded language, capable of executing one task at a time. This creates an immediate engineering challenge when dealing with high-latency I/O operations, such as pulling large datasets from a remote server. If JavaScript processed these requests synchronously on its single thread, the engine would have to wait for the network to respond before moving to the next line of code. The interface would freeze until the data arrived. To function in modern environments, JavaScript requires a mechanism to process thousands of requests simultaneously while confined to a single thread. This blueprint details the Royal Research breakdown of the JavaScript concurrency model, a framework designed to solve this single-thread paradox. The core thesis of this framework is that JavaScript achieves concurrency through precise architectural orchestration rather than parallel execution. The central mechanism driving this orchestration is a continuous monitoring system known as the event loop. While parallel multithreading assigns tasks to separate hardware lanes, JavaScript relies on an emergent concurrency model, shifting tasks between different structural components to avoid blocking the main thread. To understand exactly how the engine prioritizes these tasks, we must reconstruct the runtime environment from first principles. Navigating this orchestration framework allows for the precise management of system resources, ensuring application performance scales with the complexity of the code. We begin with the foundational execution component of JavaScript engine, the call stack. This data structure keeps track of function calls using a last-in, first-out mechanism. When a function is invoked, the engine packages that task into a block and pushes it onto the top of the stack. Once the function completes its execution, that specific block is removed, or popped, from the stack. This strict push and pop mechanic guarantees that JavaScript executes code in a sequential, synchronous order. Tracking a simple synchronous script shows this in practice. As the engine reads each line, the corresponding function pushes onto the stack, executes, and immediately pops off. As long as the tasks are computationally fast, the stack operates smoothly and the application remains responsive. However, the call stack alone is architecturally insufficient. A single slow network task at the top will halt the pop mechanism, preventing any subsequent code from running. When a high-latency network request hits the top of the call stack, the entire sequence freezes. To prevent a total freeze, the engine relies on the external runtime environment. In a browser, these are the web APIs. In Node.js, they are C++ APIs. JavaScript does not wait for the high-latency operation to finish. Instead, it delegates the task, handing it off to the external environment. This handoff frees the call stack to execute the next synchronous line of code immediately. While the script continues running on the main thread, the external environment processes the I/O task, such as fetching data from a server, in the background. Non-blocking behavior is achieved by evicting the blocking element from the main thread's jurisdiction.
This delegation requires a method for the external environment to return completed data to the main thread once the background task finishes. The architecture relies on task queues. These are holding areas for callback functions containing the returned data. The first holding area is the macro task queue. It handles standard callbacks from events like setTimeout and routine I/O operations. Modern asynchronous programming also uses promises, which represent values that may be available in the future. Promises require a second holding area, the micro task queue. This is dedicated exclusively to resolved promises and other high-priority microtasks. The engine applies a strict priority rule. Microtasks act as a fast lane that preempts macrotasks. The engine is programmed to drain the microtask queue until it is completely empty, before it is allowed to process a single item in the macrotask queue. Predicting this execution order is vital. An endless stream of microtasks will starve the macrotask queue, preventing critical I/O callbacks from ever executing. To connect these waiting queues back to the active call stack, JavaScript uses its final arbitration mechanism, the event loop. The event loop monitors the system and activates only when the call stack is completely empty. Once the stack clears, the loop routes the microtasks. It pushes these high-priority blocks onto the stack one by one until the microtask queue is empty. The loop then addresses the macrotask queue,
pulling exactly one standard task and pushing it to the call stack before stopping. After that single macro task executes, the loop resets. It rechecks the microtask queue to ensure no high-priority promises resolved during that brief execution window. By enforcing this sequence, the event loop balances the immediate execution of internal logic with the steady processing of background system events.
This code comparison bridges the abstract architecture to modern tooling. On the left is traditional promise chaining. On the right is the modern async await syntax. Using async and await is not a bypass of the architecture. It is syntactic sugar built directly on top of the existing promise structure. Every async await command compiles down to promises, meaning these operations are still routed through the high-priority microtask queue. This syntax allows developers to write asynchronous logic that reads top to bottom, mirroring the appearance of a synchronous script. Despite this visual flow, the underlying execution relies entirely on the non-blocking mechanics of the event loop. Modern syntaxes simplify the developer experience, but they require a deep understanding of the strict queuing system operating underneath. When we view the complete system, we see the call stack clearing functions, the external environment absorbing I/O tasks, and the event loop arbitrating the returning data queues. This view reinforces the core insight from Royal Research. JavaScript concurrency is a maintained illusion driven by high-speed delegation and rigorous queue arbitration. Internalizing this execution trace equips developers to accurately predict execution order, trace complex bugs, and prevent application bottlenecks. The efficiency of an application is dictated by the interaction between the source code and the orchestration of the loop itself.